We'll kind of just start. Thanks everyone for participating in this NISS Merck webinar. Today we are fortunate to have two prominent speakers to share with us their contributions and visions regarding interpretable and explainable machine learning. And each speaker will give a 35 minutes talk, and then we will have around 7 minutes to ask the speaker some questions at the end, or you can provide your question during the talk in the chat channel. Today, kind of due to with the help of James and Megan, this webinar became possible. And so today our first speaker is Professor Cynthia Rudin. And Cynthia got her PhD from Princeton University in 2004. She is currently a professor of 4 different departments at Duke University, including computer science, electrical and computer engineering, statistical science, and biostatistics and bioinformatics. She is also directing the Interpretable Machine Learning Lab at Duke. Cynthia is the recipient of a long list of award and recognition, including the 2022 Squirrel AI Award for Artificial Intelligence for the Benefit of Humanity, which is like the Nobel Prize of AI. So without any further delay, Cynthia, you can start your talk when you are ready.
Thanks so much. All right, so so my name is Cynthia and I work in interpretable machine learning. I started working in this field because I was working with the New York City power company trying to predict power reliability issues. And I realized that more complex machine learning models were not giving me any better predictions than very, very simple models. And I thought that maybe like the problem that I was working on was an anomaly, but it wasn't. Like the same thing kept happening again and again. So here's another example. So back in 2015, we wrote this article called Interpretable Classification Models for Recidivism Prediction. And in this article, we used the largest public data set on criminal recidivism. It was like 30,000 or 33,000 people all released from prison in the same year. And we used interpretable machine learning and black box machine learning to predict whether someone would commit one of a bunch of different kinds of crime after they were released from prison. So these are like misdemeanors, violent crimes, sexual crimes, violent crimes, I said that, property crimes, drug crimes, you name it. And what we showed was that you don't need a complicated model to predict recidivism, and race is actually not a useful variable for predicting recidivism. And so we were very surprised when, 6 months later, the ProPublica article came out and said that there was this proprietary model used in the criminal justice system in the United States, and it uses race. And we thought, race doesn't even predict recidivism, so why would they use race? And then second, these types of models should not be proprietary because they determine people's freedom. So we were wondering, like, how accurate is this model anyway? Like, is this really better than what we've, put in our paper? So, how accurate is this? And so we did a comparison of the COMPAS scores from the ProPublica article to an algorithm that we developed at the time of the dataset release, which was called Corals. Corals is a very complicated algorithm, but it produces really simple models. And so it produced this model on the Florida data, and we looked at it and thought, oh, that's really quite simple. Could that really be as accurate as COMPAS? And surprisingly, it was. This is results from tenfold cross-validation, and they're about equally accurate. And so then we thought, okay, well, we don't know why we need proprietary models in the justice system, but also, like, can we get any more accuracy? Like, can we actually do better than this? So we threw the whole machine learning arsenal at the problem, and none of them did any better. And so there was this like huge debate about algorithmic fairness and COMPAS and so on, but I think it was all misplaced. I think the truth is that we just don't really need COMPAS. Anyway, as it turns out, this is not the only data set where simple models perform well. In fact, it happens really often. So let me show you another example. This is a high stakes decision in healthcare where, like, let's say that you have an aneurysm in your brain, so something like that, and it bursts, and so you have like a brain hemorrhage, like you have a blood explosion in your brain here, and then you would be sent to the hospital, you'd get surgery, you'd be placed in the intensive care unit, and you would have EEG monitors placed all over your head to detect for the possibility that you might have a seizure. And seizures are common. In fact, 20% of critically ill patients get them. They cause brain damage. And the only way to detect them is with EEG. So if this was you, there's a reasonable chance that at that point, doctors would score your risk for seizure using the 2 helps 2B score we designed, which is so small that it fits in the corner of a PowerPoint slide. And the name of the model obviously comes from like 2 HELPS and then 2 points for the B. So the doctors can memorize the whole model just by knowing its name. This model was designed by an algorithm for interpretable machine learning, where the selection of features and the point scores get chosen by the algorithm. It's just as accurate as black box models on the data set. It's led to a substantial reduction in the duration of EEG monitoring per patient, which allowed the doctors to monitor a lot more patients and reduce brain damage and save lives. Now, it seems, though, then that there's no benefit from complicated models for lots of problems. Here are applications that I've worked on where in none of these cases we needed a black box model. So it could be, like in the case of Compass, that we're often relying on complicated models for high stakes societal decisions when we don't actually need them. Now, there's a bit of nuance to what I'm saying here, which is that there are really 2 fundamentally different types of problems that we encounter in machine learning. And they're like 2 totally different fields almost of machine learning. And the whole thought process between them is like night and day. So like with tabular data, you have a good representation of the data and the features are interpretable, whereas raw data are like, images or sound waves or text, something like that. For raw data, you really need a neural network. It's the only type of method that's working right now. Whereas with tabular data, as long as you're willing to do some pre-processing, all the methods tend to have similar performance like I was showing you. And that includes even very, very sparse models. Like raw data is just fundamentally different. Like it tends to live on these like thin manifolds in feature space. So for instance, with images, if you just change like 1 pixel in an image, it no longer lives on the natural manifold of the manifold of natural images. Like it's actually out of distribution at that point. And tabular data is not generally like that. Like it's usually not that sensitive to changes in the data. Like if you change your exercise or allergies or whatever, like that, the resulting feature vector would still be realistic. So we were wondering, like, why is it that we're just not getting any benefit from complicated models here, right? It seems like there should be some benefit to adding lots of extra complexity to these problems, but it doesn't really happen with tabular data. Like as soon as you start adding more complexity, you just overfit. And I have a theory as to why this happens. It's a very simple theory. And my theory is that there are just lots of good models. So let me explain this theory a little bit more. So my theory is called the Rashomon set theory. And the theory is that, like I said, like there are just lots of good models. So if you think about the set of all models, think about like a large number of them being good, maybe not half of them, but like still like a large number. And then this set should be large enough that it includes like a ball. Okay, so the set of good models is big enough to include a ball of good models. And then if the set of simpler models is a good cover for the set of all models, then the idea is that if the good models contain this ball and the simpler models is a good cover, then at least 1 point in the cover ends up in the ball. So you have at least 1 simple model that is also good. That's the idea. And this notion that simpler models is a good cover for all models, I think that's totally reasonable because, for instance, like sparse decision trees are a good cover for the set of all trees, and trees are universal approximators. So I think it actually makes sense. So let's call this set of good models. I'm going to call that set the Rashomon set. Okay. So the Rashomon set, this is the set of models that are all about equally good, right? And you can't, not one is better than the other. They're all about equally good. And these are models that have like loss that's very, very close to optimal, okay, on the data. And now I claim that the Rashomon set is large in many of the types of problems that I consider. So the paper that I'm going to tell you about, this paper, this paper has a lot of very computationally heavy experiments. We were trying to, assess this theory here. And we actually calculated the size of the Rashomon set, or well, maybe like this ratio of like good models to all models. We calculated that for like 70 data sets for decision trees. And we tried to correlate that ratio of this, the amount of good models. We tried to correlate that with lots of different things. And what we found was pretty interesting. So what we found was that large Rashomon sets are correlated with the existence of simpler models. Okay, not a surprise if you buy this theory. But we also found some other stuff, which is that many different machine learning methods having the same performance is correlated with large Rashomon sets. Okay, so why would that be? And the way I think about it is that you have lots of different models, so models that are different, types. For instance, you might have some models with linear models, some are Gaussian models, Gaussian kernels, maybe decision trees, forests. And the idea is if they all perform the same, then the Rashomon set is large enough to include all of those good models that are very different from each other. And so it's got to be kind of big. Okay, so that's that idea. And then the third result was that large Rashomon sets are correlated with more label or feature noise. So these are problems where the outcome is hard to predict. So for something like criminal recidivism, for instance, it is really hard to predict whether somebody is going to commit a crime within 2 years after they're released from prison. Like there's so much randomness in like that person's life that it creates this intrinsic level of noise in the data. Okay, so the implications for this theory, if I'm right, and there are just lots of good models for most tabular data problems, the implication is that optimizing for simplicity actually won't sacrifice accuracy. And if I'm right, this has huge implications for a lot of high stakes decisions that are made using data in our society that deeply affect people's lives. And that includes criminal justice decisions that determine people's freedom, like loan decisions that determine someone's ability to purchase a home, or medical decisions that determine life or death. Okay, so if I'm right, then for none of these decisions can we really justify the use of black box models. For none of them. Okay, so now this theory kind of reveals like why we were able to find accurate models for these data sets without losing predictive performance. It's because these data sets probably admit many good models, right? They're all tabular, they all have noise because we're predicting things that are inherently difficult to predict, okay? So let me go back to the results from our fact paper. And I wanna just focus on this result for a bit because it's pretty useful, okay? So the fact that many different machine learning methods have the same performance has a correlation with a large Rashomon set it's really useful. So what I'm saying is that if you run many different machine learning methods on the data and you get the same performance, then you can decide whether it's worthwhile to run something more computationally expensive to get a more interpretable model, okay? So I wanna tell you about a case where we did this, and that's with the Explainable Machine Learning Challenge. So FICO gave us this data set about loan decisions, and they said, make a black box and explain it. And the question is whether we need to do that. Okay, so we got this data. Like I said, it's loan decisions, 10,000 loan applicants, tons of information about their credit history. We tried a bunch of black box algorithms. 73% is the best you can get. And I thought, could it be a tabular data set where you don't need a black box? And so I asked my students to do some experiments. I said, look, can you please run lots of different black box algorithms on the data set and see if they all perform about the same? And the students came back to me about 2 days later and they said, yeah, they all perform the same. So at that point, I knew we probably didn't need a black box for this data set. Like I was pretty certain that you could get an interpretable model at the same accuracy, okay? Now, at the time of the competition, we didn't have the tools that are available now. So Yeah, so I get the benefit of telling you about these results after having developed these algorithms, and I'll spare you the details of the first few tries we had at this data set and how long it took to do it. So you get to see like 2022 algorithms in action instead, okay? And the first algorithm I'll talk about is fast sparse. So fast sparse produces sparse generalized additive models, which are an alternative to logistic regression. And it is fast. And so just to give you a sense of its performance, so this is the best of the black box. So best accuracy, 73%, best AUC, 0.8. And fast sparse takes less than 20 seconds. It gets you to the same accuracy and AUC as those black box baselines. And then the difference, of course, is that it gives you interpretable models. And in fact, I can actually write the whole model on a slide for you because the whole model fits on a slide. All right, so this is the fast sparse result on the FICO dataset. That's the whole model. You get a score for each of these features and you just add them up. Okay, so let's take a look at some of the factors here. So months since oldest trade open. So here, if your oldest trade hasn't been open for like very long, then you get more risk points than if they were open longer. And number of satisfactory trades. Like if you don't have very many satisfactory trades, then you get more risk points. And then like external risk estimate. This is probably the most powerful feature, and it's very sensitive between values like 60 to 80, okay? So you just add up the points you get from all these factors. It just translates into a risk. Okay, that's it. It's just a table that translates it into a risk. Now, what's really shocking about this model, besides its simplicity in describing this difficult benchmark data set, is that we created it in under 4 seconds, right? And that's how fast this algorithm runs on average on this data set. It's about 4 seconds. Now, this competition, as I said, they told everyone to create a black box model and explain it. And they told us to do this because they didn't know that it was possible to create a model like this at all. And we did it in under 4 seconds. All right, so let me tell you about the machine learning method that created this really sparse model. And I'm going to start with sparse logistic regression, which minimizes the logistic loss with L0 regularization. Right, L0 is better than L1 because it doesn't give you the bias that L1 creates when you sort of jack up that regularization. And then, of course, the model is linear. And then it translates into a conditional probability using the standard formula for logistic regression. Now to get so far this is all standard stuff here. But to translate, to sort of get a generalized additive model, then the best way I found to do this is through pre-processing the data. So if you have a continuous variable, then you transform it into a bunch of binary variables like this. So you've just basically put thresholds in between each of the realized values in the data set. And then the thing is, you've now blown up the feature space, right? You have a lot more features, but you can, if you take weighted combinations of these variables, you can create these really flexible functions of age, since, right, logistic regression gives you a weighted sum of these dummy variables. So you get these kind of like component functions that are pretty funky there. Okay. So, and like the vast majority of machine learning methods, we're gonna, to minimize the objective, we're gonna use some variation of gradient descent. We're using coordinate descent where you optimize one coefficient at a time. And since we want models that are sparse, we're going to try to send coefficients to 0 very often. Like we're just continually kind of pushing coefficients to 0. Okay, so we came up with a few ideas for this. We have a method that uses cutting planes and quadratic cuts for solving this thing. And it was fast. But later we figured out a way that was simpler, and it didn't use cutting planes and it didn't use quadratic cuts. And it involved changing the problem just very slightly. Okay, so here, logistic loss, I'm going to change this to exponential loss, okay? So same exponential loss that's used in AdaBoost here. And then AdaBoost, luckily, the exponential loss, luckily, has this formula that's actually very close to logistic regression's formula for producing a conditional probability estimates. Okay, so everything's going to be almost the same as logistic regression, just going to be exponential loss instead of logistic loss, okay? But the great thing is that there's a huge difference, which is that if you use exponential loss with dummy variables, like what I created, then it has an analytical solution for the line search at each step of coordinate descent. So you just go from wherever you are straight down to the minimum using a formula. Okay, and the formula looks like this. And I know it's kind of a crazy formula. It's like if this happens, then do this. If this happens, then do that. But there's no cutting planes. Like it just goes directly to the minimum right there. Okay, and that makes the whole thing really, really fast. So at every iteration, we just update one of these W's here, and just using the formula on the previous slide. And then we use a priority queue to keep track of like which W's we want to update, keep updating next. And then we just keep updating it until it's converged. And then we get these very sparse models very, very quickly. Okay, so back to the FICO dataset here. So the algorithm transformed the dataset into over 1,900 binary features, and then iterated through subsets of them. And then, yeah, created 21 of these total step features in just a few seconds. Okay, so far during this talk, I have explained to you the idea of the Rashomon set theory, which is that simpler models exist when there are a large number of almost optimal models. I've talked to you about the results from the fact paper, which is that if you run a lot of machine learning algorithms and they all perform similarly, could be due to a large Rashomon set. Also, if you try to predict outcomes that are uncertain, right, have a lot of noise in them, probably are in the case of a large Rashomon set. And if you do have a large Rashomon set, algorithms like fast-sparse can probably find a sparse accurate model. And in fact, even on competition data sets like the FICO challenge data set, we find interpretable models that can be shown to you on a PowerPoint slide. Now, this of course has huge implications for criminal justice, loan decisions, and other high stakes decisions, because in these cases, our theory makes it harder to justify the use of a black box model. But I am not done yet. Now, it's worthwhile to point out here that lots of machine learning people don't want to hear about this, right? They are just not interested, right? The idea of producing simple models are really not what mainstream machine learning has been focusing on. They are and have always been like focused on building more complex models, right? Mainly for computer vision, and they're interested in preventing overfitting. Now, I'm going the other way. Like, I want to know how simple you can get and still maintain performance, right? I don't need to prevent overfitting. My models aren't going to overfit because they're simple, so they don't overfit, right? Statistical learning theory tells you that. So it's really a different perspective on machine learning than what most people have. And a lot of people, like, they just don't believe me. Like, no matter how many little tiny models I put up on the slides, right? No matter how much proof I give them, it doesn't matter. Okay, so anyway, let's go to the next topic, which is sparse decision trees. So decision trees have been popular since the very beginning of AI. And the main problem that's always plagued decision tree algorithms is their lack of optimality, because they've historically been these greedy, myopic algorithms like CART and C4.5 that sort of build trees from the top down and greedily kind of prune them back afterward. And the problem is that if a greedy algorithm chooses the wrong split at the top of the tree, then there's no way to undo it. Like, if I'm trying to predict whether I'm going to get stuck in traffic on my way home from work, and maybe rain wasn't the best first question to ask if I want a small tree, but a greedy algorithm picked it, so now I'm stuck with it. Anyway, so these greedy algorithms produce suboptimal trees, but it's really hard to improve over the greedy methods because decision tree optimization is really hard, both theoretically and practically. It's actually NP hard. It's factorial in the number of variables, which is kind of like exponential. And so that's why people, have since the 1970s been mostly working on building kind of these greedy trees. So lately, though, this has been a very popular research area for some reason. And, I've been working on it for about 10 years. I already showed you the corals algorithm earlier. And the latest method that we've produced is called GHOST, and it uses dynamic programming with bounds that reduce the search space. And I'll just put up the army of people that we have that are working on GHOST. GHOST is very fast. It's much faster than the previous approaches for optimal sparse decision trees. And this is like one of the problems that it solves, which is kind of minimize misclassification error, balanced with sparsity. It just tries to have like a small number of leaves and keep the model accurate. And when you solve problems like that to optimality, you get sparse accurate trees like this one this is back to the Florida rearrest data, the same one that ProPublica used. So this one would say like, do you have more than 3 prior offenses? If so, predict arrest within 2 years of, your compass score calculation. Otherwise, ask you about your age and so on. Now, GHOST is a dynamic programming algorithm. So, there's a lot of sub-problems that are involved in this. Like if you ask, what is the best split for the top? Well, to figure out that best split, you have to figure out the best optimal split beneath it. And then to get that one, you have to figure out the optimal split beneath that and the one below that. And then eventually you'll be able to figure out that the optimal solution for a subset of data, like the optimal tree, is actually just a leaf. And then you propagate that information back upward through the problems until you get the optimal solution for the very top, for the root node. Okay, so a subproblem. The goal of a subproblem is to find an optimal tree for a subset of the data. And that subset of the data is represented by a binary bit vector, a binary vector, like a bit vector in GHOST. So here, for instance, is a bit vector, and it's of size n, where your data set has n data points. And it tells you which data points are involved in the subproblem. So here it says that data points like 1, 3, 4, 6, and 8 are actually in the subproblem that we're working on. Like maybe we're sort of somewhere over here and we're working on a subset of data. This is the subset of data that defines the problem that we're working on. Okay, so what GHOST does is it starts from the master problem, which has all the data points in it, so vector of all ones of size n, and then it constructs this dependency graph like that. It considers all possible splits for the top. So you've got all these possible splits for the top that are all being considered. And then this dependency graph includes all of the subproblems that GHOST encounters throughout its run, okay? So it's trying out all different possibilities for the top, and then it tries out all different possibilities for the second, split given the top split, and then so on and so forth. So here, these are all possible splits for the top. And then here are all possible splits for like, one down and so on. Okay, and then for each subproblem, it tells you which data is involved in it, and it keeps track of like upper and lower bounds on the objective for the subproblems. And then it cycles through these subproblems according to a priority queue. And then after it solves a subproblem, it passes that information back upward, up to the top of the dependency graph to all the parents. And so it very rapidly searches through subproblems, adds subproblems to the graph, and then if it solves the subproblem, it passes the information back up so that you can tighten all the bounds and then solve it faster. So the graphs can get really, really big, but we can prune them efficiently. So we'll go back to the FICO data set, which is my sort of muse today. And you can look at this tree. This is from GHOST. It's an optimal sparse tree for this FICO data set. And the first thing you want to notice is that it has only 10 leaves, only 10 leaves. And its accuracy is just, right about close to the best of the black boxes. And we uncovered it in less than 10 seconds. And the tree is actually meaningful. So if you look at it, it first splits on this external risk estimate, which we know is a very important feature. And it says, if the external risk estimate is really low or really high, then I know what to do. And then otherwise, like in that kind of sensitive region of external risk estimate, then I'm going to ask you like some more detailed questions, like what percent of trades do you have with balance, and how many months, what's your average months in file, and so on. And so, yeah, so again, just to remind you, this is not an easy data set, right? This is a benchmark data set, and we did not know that it was possible to construct a single tree with this level of accuracy on this data set. And in fact, without Ghost, I don't actually know of another way we could have done this, because I didn't know we could get to this level of sparsity and maintain kind of black box performance. And so this is the type of result that we're aiming for, and I'm actually thrilled after all these years that we managed to get there. Okay, so I hope you're getting closer to understanding the implications of the existence of interpretable models, which makes it hard to justify the use of black box models for high stakes applications. But there's a lot more to this story here, and there's something that's been eating at me for quite a while, which is that something is broken. What the machine learning world is trying to create is clearly not what the world needs for high stakes decisions, right? We need models that are trustworthy, like things that you can criticize, things that people can easily double check, right? Because for high stakes decisions, black box models they're just not going to cut it. But guess what? My simple models are not going to cut it either, because the whole paradigm of machine learning is just wrong for these problems. So let me explain what I'm talking about. So the kind of universal paradigm for machine learning is that you take a training set, you send it to an algorithm, it minimizes the loss, produces a predictive model that predicts Y from X. Okay? That's just the way this is the way it always is, right? This model could be a decision tree, could be a random forest, could be a neural network, linear model, support vector machine, could be kernel regression, could be a generalized additive model, whatever, okay? This is the standard approach. We do this for essentially all machine learning applications, right? Even for self-supervised applications, that's the way it is, right? You predict some Y from X using one model, okay? And this is really a universal way that all of machine learning is set up, but I claim that it's fundamentally flawed and that we should totally reconsider this for high stakes decisions. Okay, so here's why. So these are domain experts that I work with on different applications. Dan Wagner, I worked with on crime series analysis. These Fides and Joseph, I work with on computer-aided mammography. Xiao, I work with on wearable devices and heart monitoring. Dave and Ed, I work with on HIV analysis, HIV reservoir analysis. And then Brandon, I worked with on the 2 helps 2B score. And the thing that's common to all of these people, even though they're very different from each other, is that they've all at some point told me that I was wrong. So when you work with domain experts and you go to great lengths to build them a model they can criticize, they will do it. They'll say, I think something's wrong with this model. Can you build one that doesn't depend on this variable in this way? Can you build one that doesn't depend on age so much? Can you incorporate fairness constraints and maintain performance? Or can you just please tell me what else is out there? What are the other options? Now, the whole premise of the Rashomon set is that there are probably a lot of good models. And there are probably a lot of simple models too. And if that's the case, why are we giving them just one model? Why don't we let the domain experts choose between these models? If there are large Rashomon sets, let's give the domain expert the whole thing. So I propose a new paradigm for machine learning. And the idea is that it's somehow something that's more human-facing than standard machine learning, which is to hand the user the whole Rashomon set, right? Hand the user lots of good, simple models, not just one model. Let them choose what they want to pick. Something that agrees with not just the data, but also their domain expertise. So instead of the algorithm producing one model, it produces all of the models that achieve low loss on the training set that are interpretable. So this is my proposal for a new paradigm for practical machine learning. But how do we get this to work? So let me show you our attempt to do this. This paper, which was just accepted very recently, actually solves this problem for sparse decision trees. It's an algorithm called tree farms. and it produces all almost optimal trees. And it's pretty amazing. Like, even to find one optimal sparse tree is NP hard, but this algorithm finds all of them in minutes, okay? And it's implemented in Ghost, so it leverages Ghost's way of representing subproblems as bit vectors. And it uses all of Ghost's graph dependency ideas, but it also has a really interesting way of keeping track of subproblems. It actually stores all the trees in a kind of an implicit way, so that you don't actually enumerate the whole Rashomon set. It just tells you how to combine different parts of different trees to get all of the optimal or slightly suboptimal trees to get the whole Rashomon set. So you can actually loop through the whole Rashomon set. So even if the Rashomon set is absolutely huge, you can still store it and work with it. So I'm going to show you tree farms. So this is the work of a brilliant young human-computer interaction expert called Jay. So I'm going to just stop sharing this screen and then switch over to the TimberTrack screen. And so here in TimberTrack, and this is a public website, by the way, it's just a public website. And I've just gone here, and I'm just going to start it from the beginning. And this is storing all of the trees that are in the Rashomon set for the Compass data set. This is the same data set from ProPublica. So this is every optimal and slightly suboptimal decision tree. So if you want to look through them, you can look through them by leaf, actually. So you can walk down a leaf. So here, let's say that I want to look at a tree whose top split is the number of prior crimes bigger than 3. And then maybe I want my next split to be on age. Like, I think age is like a good thing to split on or something. And then maybe I'll split on, I don't know, just pick something, whether they've had any juvenile felonies. And then from there, I can grab a tree, and then I can store it over here. I can write a little note saying, like, I like this tree. If I can spell, I like this tree. Great. And then you can also, like, put a little heart on it if you want to. You can also, like, visualize the tree with telling you how many data points, like what fraction of the data points are in each leaf. And if you decide you don't like that tree, you can go back to the beginning and just, pick another tree, do whatever you want. You can just explore the Rashomon set. You can just, let's say you want to go here and you pick this tree, there you go. You can save that one as well, whatever you want to do. So it's kind of a much more like human-facing way of approaching interpretability and machine learning. All right, so now hopefully we can, provide this more useful thing to practitioners. And this is where I think that we should be focusing on these sort of more kind of human-facing questions for AI. Okay, so just to summarize, I talked about the Rashomon set theory, the fact that if you run different algorithms that all perform similarly could have a large Rashomon set, uncertain outcomes lead to large Rashomon sets. I talked about 2 algorithms for producing optimal models, or optimal sparse models. So fast sparse for generalized additive models and Ghost for decision trees. And those algorithms work even on these benchmark competition data sets where people didn't actually know that you could produce interpretable models. And this has huge implications, as I mentioned, for lots of high-stakes decisions. And I think that's true particularly if we can provide users the freedom to choose among these models, like I showed with tree farms. All right, and thank you very much.
Thank you so much, Cynthia. This is wonderful. So we do have some questions, a lot of the questions listed, but we may not be able to cover all of them. We will cover some of them. So the first one is does the proposed new paradigm move the problem from potential overfitting to potential overinterpretation? I'm not fully understanding this question, but I don't know whether you can understand and address something here.
Well, I mean, if you ask domain experts to look through these models, they know what they're looking for, right? They know that these models don't make sense, and they know that these models do make sense. Because, there's always uncertainty in the data, right? These data sets are not infinite. And so, and the data sets also don't, like, not only do they have they have a finite number of examples, but they also have a finite number of features. So there's only a certain amount of information that can be contained in any data set. So you need the domain experts to kind of fill in that missing information. So I don't understand where this question's coming from, because, you know, if you work with domain experts, they know what they're looking for. Unless maybe you're not working with the right domain experts. My ones know what they're looking for.
Right. There is another question that I suspect that the comparable performance of simple models has something to do with the fact that the outcomes are binary in the examples. Any comments here? Basically saying like
that large Rashomon sets are because you're working with classification data? I don't know.
That's the implication of the questions, right?
Well, I mean, you could be right, but the thing is, there are lots of classification problems. So, you know, yes or no questions are sort of pervasive throughout society, right? Is this person going to commit a crime or are they not? So, I mean, even if you're right, even if maybe other types of problems don't have large Rashomon sets, the types of problems that do have large Rashomon sets are really matter. You know, like, are you going to repay your loan or not? So, I mean, I take your point, but I think my point is still completely valid.
Yeah, there are a lot of questions about are there any kind of available R or Python package available for this kind of method you are mentioning here?
Yes, so Ghost is available in R and Python, and we now have an implementation that works for Windows as well. FastSparse it's an R interface to C++ code. So, and we're going to be working on a Python interface for that soon. And then Tree Farms as well uses Ghost. So we're still working on implementing that more broadly. But if you're a pretty well-rounded programmer, then you should be able to use any of them. They're all public.
Yeah. I think that covered most of the kind of important questions here. Any other things you want to kind of see, Cynthia, before the end of this the first talk?
Okay, so should I try to answer some more of these questions, or should I just give up? That's a lot.
Some of the questions, I think, after you continue your presentation, they may, for example, they ask a particular method, how that is done. My understanding is they may understand that after you finish your presentation, or they can read the paper or later on. Yeah.
Okay. Well, anyway, great, cool. I'm glad I've answered as many questions as I could.
Thank you so much. Okay. Thank you very much. Yeah. Let's move on to our next speaker, Professor Bing Yu. Bing got her PhD from UC Berkeley, and she's currently the Chancellor's Distinguished Professor in the Department of Statistical and the Department of Electrical Engineering, Computer Science, and the Center for Computational Biology at UC Berkeley. She has published over 170 publications in premier venues. Those papers not only investigate a wide range of practical and theoretical research topics, but also seek deep insights. I mean, the breadth and the depth of her work enable unique and novel solutions to problems in audio and image compression, network tomography, remote sensing, neuroscience, genomics, and precision medicine. So Bing, you can start your presentation when you are ready.
Thank you for having me here. So it's kind of nice to follow up Cynthia's talk, because I'm going to move to the more raw data and the complex models and try to, I believe that these also have huge values, but I do like interpretability, and we try to actually interpret these deep learning models. So this quote I like a lot by Bill Gates: AI is like nuclear energy, both promising and dangerous, and data science such a driving force behind AI. And therefore both AI and data science have this both promise and dangers. I have always grounded my research, at least the last 20 years, in very close collaborations with scientists. There was an earlier comment, I think Cynthia answered. Maybe I'll give a little different view than that. I think the question was quite valid, that I don't trust everything my collaborator says, even the top scientists. They also have confirmation bias. Actually, so when we work with them, we actually give different results, and some random, some not highly ranked, and some high ranked, for them to help them to really get objective information out of themselves and just like confirm with what we say. So I don't feel like they always know what's the right model either. And so in the process of working with them, you need interpretation. And the data science is not just one step, it's a whole life cycle. And if we want high stake decision to be trustworthy, it's not enough just look at the final result. We have to look at the whole data science process. So EU has been leading the way to have different regulations for machines to be interpretable. There's a new one coming out called Digital Service Act, probably will be approved next year. It's really asking more specific questions about the algorithm have to have parameters can explain. Here, just like right explanations. It's getting more detail. There are many examples, I'm sure people here already, that cases where we need interpretation. So I'd like to introduce the concept of scientific machine learning. I think interpretation is especially necessary for scientific machine learning, which are defined as use machine learning to do science, but at the same time build scientific principles in machine learning algorithms. And you iterate between the two steps, and results are subject to scientific standards. And we need open source and reproducible software. So we have been struggling to define, I think interpretable machine learning is really frontier machine learning. Machine learning also has been moving that, what do we mean by interpretable machine learning? So about 3 or 4 years ago, I had my group of people, Jamie and Chandon, Risa and Carl. So Chandon now is at Microsoft Research, Risa faculty at UCSF, and Carl is a postdoc at UCSF, and Jamie is doing his own startup. So we put our heads together. We're working on different problems, just machine learning, neuroscience, and also genomics, to say, really put something that we can agree on. So when we discuss interpretable machine learning, we can know what we talk about. So the key is to actually introduce relevance and problem. So you need reality check, which is predictive accuracy on a proper setup test set, which I'll get back to later. And also you need descriptive accuracy. That's where domain experts comes in to really help you what are trustworthy domain information and whether the different models make sense or not. But you want to give them also good and bad models so that they can really test that they can tell them apart instead of they just confirmation bias agree with you. And relevance is very much defined in context. And even with the same data, with different downstream usage of the model, the relevance will be different. Are you just going to do more basic science or is high stake decision making? I think the relevancy is not exactly the same. Most of the time, people think that our decisions are most interpretable, as you've seen plenty in Cynthia's talk. Logistic regression also was there. And then you go to random forest, and people think there's a trade-off. What I will show you that's not always the case. Depends on how you work with these models. Of course, this is for image data, what Cynthia called raw data. We really had a huge research surge on deep learning models, right? ImageNet play a huge role in the advance of machine learning, computer vision, and that's already 10 years ago. But the most recent development is actually, we move away from the architecture of convolution networks to transformers. It's more modular, and in some sense, there are different parts you can understand, and huge advances in these large language models with summarization, question answering, translation, and many more. And also, people are also translating using similar model for genomics, right? Because genomics at DNA level, you have really discrete data and has lots of similarity in some sense with the language data. People also generalizing to vision transformers. So you can see that the performance is really leading now by also transformers. And the biggest advance and got every scientist to take notice is the AlphaFold 2 that really beat significantly all the other competing methods, and people are now building on top of that for basic science. So these complex models for complex problems are making real advances in the midst of a lot of hypes. So the question becomes, we want to trust in interpretable deep learning or machine learning. Where does the trust come from? Great top scientists, you want to have them to introduce the domain knowledge in collaboration with statisticians, machine learners, and data scientists. And this really is building on accumulation of trustworthy or factual empirical evidence. So algorithms are mental constructs. We really need empirical or objective validations of what our knowledge is, and including the knowledge from interpretable deep learning and machine learning models. That's like at the downstream, after you have the model, you hope you agree. But I think we really have to push upstream to look at the whole data science process, because your test data often is already subjected to human data curation and cleaning. So if that step, you already got yourself very unrealistic clean data, you won't discover that until you go upstream to see how the data cleaning was done. And humans usually don't clean data in the same way. And that's a very important overlooked area that counts for a lot of the uncertainty and non-reproducibility, a lot of the scientific results, which we really need to really include this process in the uncertainty accounting than just after the data is cleaned, and then also use clean test data to validate our results. So for the rest of the talk, I will start with this I'll call out of context methodology development led by Jimmy Murdoch and later joined by Chandan Singh to really try to interpret deep learning models. So we're struggling just as machine learner in the beginning for sentiment analysis, want to really take a look how the predictions are made. And then we engage with cosmologists to really understand their problem, their relevance, and use our ACD, which is out of context development, and bring to in context. And in context, we develop the adaptive wavelet distillation to make very complex model simpler and more interpretable. At the same time, actually, we'll also improve the prediction performance. And now I'll end with our PCS framework for the whole pipeline to be quality controlled, and therefore can trust the model that comes out. So the first I'll call this out of context methodology development. Jimmy was a machine learner, want to understand deep learning, and we look at how the interpretable machine learning was done, but deep learning was mostly like marginal importance. And we want to look at feature interactions. And that was the motivation. And he was working on sentiment analysis. So we use that as the beginning, and we also generalize to deep learning models now also for transformers. And then we also want to present this importance in a humanly relevant way so that people can really understand these different numbers in a way that easier for them to get understanding, human understanding. So there were two kinds of interpretation method for deep learning or for any model in general. Gradient-based in a way that it's not just applicable to deep learning, it's also applicable to any models. You basically do, for a fixed feature, you look at the gradient or integrate gradient and through some perturbation, like local perturbation, and you give importance that way. The other branch is really occlusion-based, is you remove things and see how much things changed. Sharp is really some method building on that. You fit kind of a structured model with additive and interaction terms, and then you use this surrogate model, which can be fitted for any model, include deep learning and random forest, and then use a surrogate model with more structure to interpret. And the example motivated us, or Jamie, was really you can give interpretation for not and good, but also want to have a compositionality for the feature importance. So like, I want to give importance for not good. And The process was appeared in Arclair paper 2018. Jamie and Liu, who is his Google supervisor that summer, is really quite involved. The formulas is really, we try to keep some additivity and trace. When you do a prediction in this deep learning model, you kind of combine the weights in a sensible way so you can give feature importance and for interaction features as well. So it's easier to describe in this example. I cannot show you the formulas because it's quite evolved, and the paper will give it to you. And you have this original input, not very good. And you decompose in kind of additive fashion into very good and not. I want to give a feature importance for very good. And you threw these two things in parallelly through this deep learning model and keep track of them and keep some additivity between the two streams. And then you end up collecting at the other end the importance for the relevant part and the importance for the relevant part. You report for the relevant part. So every combination of phrases, you now can have an importance measure. The question is, does this make sense? So you have to use the examples, and we later generalize to CNN, right? Similar thing, you want to see whether this region is important or not. And then you do similar things with non-trivial generalization. We first start with the LSTM, it's a recurrent neural network, but you can also do it for CNN. But then you have all these numbers floating around, right? So for any, like you look at sentence, for any combination you want, you can have this a number. That's not really meaningful, right? You have to organize them. So this is the paper when Chandon joined the project. It's really uses CD scores, we call contextual decomposition scores, as I described, to use a hierarchical clustering algorithm to organize them in a way that you can see how the different decisions are made. Well, just a simple example again. So we have scores for not, very, and good, right? And then we also have a score for very good. And you say that whether you should combine not, very, or very good, and you have the biggest jump of importance, then that's why we decide to merge very good, and so on and so forth. So this way, you know that this deep learning gives you negative for this sentence. In the beginning, it's all kind of not, it's neutral, and then very good and very good are all positive. And then it's the last joining make this phrase labeled as negative. So you kind of pin down where the decision switched and where have detailed information. But all of this, you can see is cherry picking. In some sense, it's cherry picking. And this is another cherry picking example of prediction for park. And then you find the skates actually identified by our algorithm as important. And even you remove the park, you're still going to think the skates are important because they're often correlated. So we run experiments to avoid the cherry picking. That's a big problem in actually a lot of large language model evaluation. People just cherry pick a few examples, and I think we need to do more human experiments. So the first experiment, we have 3 data sets. The SST is a Stanford sentiment trunk, and then everybody knows NISS, and then ImageNet. You can see that the first one is we created a bad model by randomizing the weights, by keeping the same label, and then used interpretation to ask the subject. This is a small experiment, about 10 to 12 people, to see whether interpretation are faithful to how good the model is, use their human understanding to differentiate. So you can see that our method gives the best performance. I mean, MNIST, everybody does pretty well. And the second one, experiment, was really to see which one is trustworthy. And there we just give you the interpretation and saying, do you trust the model based on the interpretation? You can see that our method also seemed to, because it probably gives more sensible interpretation, people also trust more. So this is really try to avoid cherry picking in papers, to have more randomized examples and for human subjects to help us decide which one is better. So now, I mean, I always want to work with scientists, and I supported the development, but my heart was always go to subject matters and really validate in science. So under my encouragement, we recruited Wu Sukha, who just joined Amazon AI, to join the project. And this is partly supported by NSF tripod grant to work with Francois Lunasi and his colleague to really see, now we have this, I'll call out of context methodology development. If we use it to do cosmology, does it help them? Does that make sense? So this is kind of external validation of the methodology development. So by that time, Francois and his colleague already had a good deep learning model to estimate so-called omega m, which is a fundamental cosmology parameter about the evolution of the universe. So at Big Bang time, this is really a description, like an aggregate description of the mass in the beginning of the universe. And then this is simulation data. They simulated using physics and PDEs forward to the purple image, which is something can be measured by something called gravitational lens telescope. So we know the truth and we pretend we don't. And we're going to use the purple image, which is observable by today's telescope, to infer the omega m. So this is very much a good sandbox for us to see whether we can get the truth. So as I said, the deep learning was not developed. It's a ResNet developed by Francois and colleagues. Gave the best result because they have simulation, they know the truth compared with all other methods. And as I said, relevance is the key, right? We work with cosmologists and we really need to be guided by what's interpretable for them. So for this particular problem, Fourier domain or the frequency domain is the more meaningful. So the first thing they said, I want you to give me importance for the different frequency domains. Luckily, our method can be easily generalized from the Fourier and inverse Fourier transform because we can have any pixels, we can get the importance. You do a linear transformation, we can still do that. So we can give importance measure for different frequency domains. And you can see lower panel is the different frequency domains. And you look at the importance measures from our now actually CD, because now have different, in the transform domain, each frequency domain become like an interaction feature, and we can give a number. And you can see that around 0.25, it gives the most importance. And this is confirmed. For this, we didn't give them some false ones, even in biology, we often do. And they believe it's sensible because it's where they believe there's a lot of Gaussian-like behavior, a lot of mass actually is concentrated in that frequency. And our importance measure also suggests high frequency like simulations might not be as relevant for estimating omega m. So this is something they could follow up. So I see this importance as not definitive, but suggestive for follow-up investigations, because we don't really, unless you have randomized trials with randomized interventions, all the importance measures, the interpretability kind of suggestive, either validated by existing empirical information, or it's a suggestive hypothesis for people to do experiments or use other domain knowledge to validate. So that's where I think we remain at suggestive. I have always wanted to connect deep learning with wavelets, something I worked on for 20 years ago. Always liked wavelets as local Fourier transform. And it's very interpretable for a lot of physical sciences people. It's really generalization of Fourier transform. And so I suggest that let's look at the wavelet domain. Can we kind of distill or get a simpler model out from these deep learning models that's something interpretable and also relevant for this physical science or cosmology. So this brings to now I'll call in context methodology development. Means that we really try to work with cosmologists closely And we already have a good predictive model, which is like I'll call the first generation machine learning really good to do, which is get predictive model. But the second phase of machine learning now is really about interpretability and more close combination with domain knowledge, very much apply statistics. And can we actually use this specific problem and develop a methodology that solve this problem and it's also generalizable, right? You see Francois here. You see also Gauko Upayayula, who's a biologist in imaging biologist, who's the head of Berkeley Bioimaging Center. And that becomes external validation, our in-context development AWD, adaptive wavelet distillation, in a completely different context of cellular biology. I'll tell you the problem a little bit. I don't have time to go into, but it's in the paper. So we basically have two very different domain areas, and this methodology developed in context with cosmology gave very similar result in a completely different problem from cellular biology. So for me, that's a lot stronger validation than just solve one domain problem. That's what, as a profession, statistical machine learning do is really general methodology, but validated with a very different context. So led by Usuka and Chandon. So distillation has been around in deep learning, you can say in general, even random forest models, that's something hard to interpret for many years now. If you can say like statistics always want to get simpler models. And the first paper, Hinton et al., at least often cited 2015, was try to go for a smaller model, smaller deep learning model from a big deep learning model. And later, people generalized to use even decision trees and additive models and to do interpretation. So relevant to our context, cosmology, we want to go to wavelet domain because people already like free domain. And independently, my suggestion, Francois actually was also talking to Wusuk and Chandon about wavelets because I didn't know that there were already wavelet-based methods for the same problem, omega m estimation, already with fixed wavelets. And so we very much converge. We wanted to have data-driven wavelet transform for improved interpretability, compression, and computation efficiency when you do generalization. So this is a very simple one-slide introduction to wavelet. It's a really beautiful, elegant mathematical theory and also very useful engineering. Right, so time series, you tile the time and frequency domain only according to time. In the free domain, ignore time and just look at frequencies. But often the frequencies actually change over time. And the wavelet transform is the orthogonal wavelet transform, so it's also invertible. Tile the time and frequency domain, I think, in a more smart way. So you can see that I'm not going to do the same frequency binning for high frequency because often high frequencies are noise or something we cannot really find or estimate very precisely. So I give bigger intervals for that. But then I cut the time so that I can allow different frequencies for different time intervals. Two great books by Malat and also Mayer. How much do I have left?
You have you still have a lot of time, like probably 15 minutes.
Okay.
Yeah.
And so wavelets also have this very nice combination or correspondence with reality, right? If you look at first layer of AlexNet, you have something quite similar to the magnetic construct of Gabor wavelets. And you also have neuroscience evidence in the late 50s to see that the V1, which are early visual cortex, act like Gabor wavelet or edge detector. So you have all this combination from wet lab experiment, from computational experiments, and also mathematical characterization. So what we did was to develop this loss function, use the fitted ResNet as for get a gradient-based interpretability. So we didn't use ACD computation, doesn't fit the PyTorch very well. So we went for the most mainstream gradient-based interpretation laws. The first one just saying that I want my wavelet to be invertible, right? I want the reconstruct law to be minimized. And the second one is the interesting one. What are we going to put to force a mother wavelet out using data? So what we did, in hindsight, seemed pretty straightforward, but it was not obvious. Woosuk and Shannon really were very creative. You look at all the formulas, right? Giving a mother wavelet is one-dimensional function, and you have a program or algorithm to just do translation and scaling to get all the different filters out. So all these filters represented by H have to satisfy all these equations if it's coming from a mother wavelet. The many equations we collected from different books, and we just put all the equations into loss functions and as L2 to make life easy for derivatives and to penalize. So that's our wavelet. We're forcing this wavelet filters out. It's kind of equivalent to the mother wavelet and with the high and low pass filters. So we went to the filter space and just find these filters. And then the interpretation loss was the L1 loss on derivatives using the ResNet and a conjectured mother wavelet. So now you can do optimization. So let's look at the result, right? Remember what I said, that people already using wavelets to do this omega m estimation. And we just use now data-driven wavelets. We call it AWD wavelet, and then plug into their method. And then that becomes our method. You can see that the AW-driven wavelet method gives the prediction error for omega n, which is continuous parameter, about 1. ResNet is 1.15, so we have like 15% reduction of error. And all the other fixed wavelets do much worse. And the last one is interesting. If we don't use the ResNet, this shows the ResNet is still useful. So it's like we have to go there, use the power of the search engine in deep learning and the structure to find good predictive model before we can come back, find a good wavelet model. If you don't use the ResNet, you get 1.3, not 1.0. So there's utility for going to the ResNet, but then we end up with now only 1,000 coefficients from the different bandwidth and coming down from 10 million parameters in ResNet 18. So this, you can see that we actually improved both prediction accuracy from 1.15 to 1.0, and we also shrank the number of parameters. So my intuition is that when wavelet, I think it's a good fit. There's something fundamental about wavelet. It's the right structure for physical phenomenon. And then wavelets allow that finer match of the analytical form with the structure of the data. And ResNet has a rougher match and led us to a good place and use that. I don't think decision tree will work here if you just fit the decision tree first and distill that. So there's this power of ResNet that we're able to harvest, and then introduces physics-based or validated wavelet structure, and we get we scored in both world interpretability and predictability. So this is the search, right? There are different wavelets. You can see more or less we find a more symmetric wavelets. And we're really doing different scaling, different location to collect the contrast between a high mass and an exaggerated difference. You remember it comes down, and that's what matters for estimating omega m. So this is a validation project. I won't have time to show you. It's really try to do a partner problem, try to understand this collagens-mediated endocytosis, where this way of cargo getting into the cell is successful or not, right? So we have two molecules we observe. We want to predict one with the other. So we also succeeded in improving both interpretability and also prediction accuracy. So here we end up with only 30 coefficients, and LSTM had 1,000, so it's become really interpretable. And this is actually the process Omicron, COVID Omicron uses. And the previous variants of COVID didn't use this process. So you can see that Omicron is super smart and just hijack the usual cargo process that we use all the time for the cell to get things inside the cell. So it's in the paper, and I won't have time to describe to the details. So this is a bad thing. So what you see here is that it's not always like this trade-off. We're able to improve both predicted accuracy and interpretability. So sometimes can go this way when you have the matching mathematical form, which is vivid for these physical science problems. So the last part is really about how can we get trustworthy quality control process instead of just look at the final result, right? I'll be very brief here. I think it's good to think about reality and representation reality, and the model is mental construct. And always keep future in our radar, because the test set should really be the best proxy for the future data. So you have different hospitals in your data set, you should not randomize. You should set aside different hospitals, because most likely the decision rules will be used for different hospitals. And if you do you have a time series, you want to set the last few years as the test set. So don't always go for randomized split. And you go to decision. Again, back to my collaborators, it's a whole data science life cycle, right? You have problem formulation, data collection, data cleaning. Every step is very important, not just about the algorithm development. I wouldn't want to be treated by a decision rule if I don't understand how the data collection is done and how it's cleaned and how every step human judgment calls are handled. So we developed this PCS framework. It's actually what Cynthia talked about tree farm. It's very much in alignment with our framework. You use predictability, but we advocate not using, we use the validation test set to decide a class of good models or reality check models, and then we consider stability. So stability is really expanded version of sample to sample variability to the whole data science life cycle. And the framework really tried to marry machine learning with good statistical practice and then expand on both. Stability is really a common sense principle, right? There's this quote by Plato saying that knowledge is prized because it's tied down than correct opinion. So stability in practice is really, we make reasonable alternative judgment calls, and we want to trace this forking of different judgment calls, including data cleaning and EDA. You use different color, you have different impressions, and document everything. And we contemplate multiple good models, reality checked models, and even multiple versions of clean data. Last semester, I had 3 teams of my class to clean the same data. They end up with 3 different clean versions. One team cleaned away 23% of the data, and they get the best result on the clean data. And that's not really transferable or generalizable when you have a real situation. And they also keep different variables sometimes. So if you think actually the many beginners' thoughts are very relevant, it's like, what's the correct way? Being a little unsure. So I like to advocate we go back to when we're all beginners, be less sure about what we do and have more doubts and try different ways and then document so that we really account fully the uncertainties than just after the clean data, after EDA, and then have a postulated probability model and go there. That's limited. It's not a full account of uncertainty, which the statistical community has been very proud of to take care of. And the climate scientists are already doing that, right? They already show you for global temperature rise, they have 9 different models, and the rise is predicted from 1.5 degree to 5.5 degrees. So it's already being practiced. These are called PCS inference to give perturbation models to really show the variability, not just under very constrained and postulated probabilistic model. Documentation is the key or a key to the process. We want to really bridge the mental construct model to reality through documentation, quantitative and qualitative narratives. So PCS is really trying to fully account for uncertainties in the whole data science lifecycle, from problem formulation. Sometimes you do regression, sometimes you do logistic regression. Do you get the same qualitative conclusion about which genes are driving a particular disease? Data cleaning, EDA choices, data perturbation choices, and also algorithm choices. And I think what's the most understudied is data cleaning. I'll call the pink elephant in the room, that it creates so much uncertainty that we don't really address it, and the PCS attempt to address it. We have software vertical flow in Python to make the PCS analysis easy, so that to parallel all the stability analysis, and you can make up your perturbations with the documentation. And to facilitate statistical inference, if you do PCS inference, you have to postulate somehow a true model to look at the coverage. And we have an R package for SimShep, and we advocate for multiple data-driven models to really evaluate in the sandbox of simulation to your coverage of either for p-values or for predictions. So we're still doing more work on AWD, and more experience is needed for adaptive wavelets, and the software is also on my website. I'm really love to go for mechanistic models from AWD. And PCS, we have many other success stories in my group using PCS for methodology development, iterative random forest for genomics, and also for subgroup discovery in clinical trials, and also for non-extreme matrix factorization for component selection. We're finishing a book, I'll say, and we have software I just mentioned, and I'm working with different centers to help to get the PCS idea into the pipeline. And we're working on PCS inference right now actively, last chapter of the book. So the book, there will be a free online copy, hope to finish this year, and with the MIT Press, with my co-author, Rebecca Butter, my current postdoc, former student. And the software packages, and I will share the slides, and I wrote a couple expository pieces by PCS, so you're welcome to read that to see the motivations. And back to the topic of decision trees for the first talk, my group actually also work on decision trees for precision medicine, digital health. And we have particular two methods for you to check out: fast interpretable sums called FIX, and also hierarchical shrinkage. For any decision tree can shrink and get 10% average mileage out for increased prediction accuracy. And the first paper is really a mathematical result showing that for additive structures, decision trees are not the best fit. You don't reach the optimal risk of convergence. And that's why we have additive decision trees. So I want to leave with this bigger question for people to think, which approach you prefer, out of context or in context? Personally, we did out of context, because my students like it, but I always prefer in context development, because I think the reality check and solving a particular problem is really powerful and actually make it more likely to be useful for another real problem. But that's just my preference. Thank you very much.
Thank you so much, Bing, for this wonderful presentation. Yeah, we do have like 5 or 6 minutes. I think at this moment, we first ask a question to Bing, and meanwhile, I think Cynthia is also available for the questions. I do have one question here for Bing. I mean, the audience asked, how can we incorporate the model objective cleaning into the process?
So the easiest way is like, you have different people clean the data with the same guidelines and write the documentation. So at least I'm advocating to keep 2 clean versions, and then run the whole pipeline for 2 clean versions. That's the easiest. And then to see whether you have a difference. And you can take the different versions, every account, I have a perturbation interval, right? So I have used one version, I get a prediction interval from 5 to 6. I use the other version, I get to 5 to 7. And then I will use 527, the bigger one, because that takes into account this uncertainty, right? We all agree that there's uncertainty introduced for different people clean data. In the future, we hope to develop a software that people actually can record easily with software, the different versions, because maybe you should do many versions, because it's not like there's only 2 versions, right? We make so many judgment calls. It could be easily 10 different versions, depends on how you do the thresholds often, right? And which variables and imputation, which imputation method you're going to use. And that's also modeling too, right? So it's a huge unaccounted for uncertainty in the data cleaning side. That's why I call the pink elephant in the room. And for big companies, I think you guys have more power to really make this, like build a computing platform and record people's decisions, and then get 2 people, even the same person, it's like, we go this way, that way. You go both ways. And then you have multiple versions. And then you can just run that down the pipeline to see and make a bigger interval. Or you say it's the wrong way to clean the data. Then you write a document about it.
Right. I kind of totally agree with this. This is statistician always consider all the data come to them is something like fixed, but indeed many things happened before the data became a spreadsheet. And we never really consider that kind of uncertainty in our kind of final result or conclusion. But that will have major kind of impact on the decisions. There is a comment here, may not be a question, but I just read it. I prefer in context. It's addressing your last slide. I prefer in context, but usually it needs more human resources. Yeah.
Yes. I definitely agree, but I think because there's so many kind of unreproducible results these days, I think that's probably a call to say that more human resource is probably needed. I do think that as a community, we produce a lot more new methods that nobody will use. And that's a waste of resource too. So I argue that's a waste of human resource. So it's better to slow down, get the right domain human resource in, and then together, actually, we do things that will be useful. Then we can do a lot of out of context methodology. That's wasteful of, data scientists, human resource. And
right.
I think it's time we should do that, because just so many new methods that not being used at all.
Yeah.
So there's another question about how proportion of time spent on each component. So that's for in-house in my group, our scientific projects usually take 3 or 4 years. So maybe it's too long for some of the industrial setting, but I think the different component can be done simultaneously or like together with different teams. So for a COVID project, I had 12 of my group members on, and we were able to develop a pretty good model in like 18 days with data cleaning, everything. So it's like divide and conquer. So the modeling team worked closely with the data team. And so you need a bigger team. The domain experts often are biased. So that's why we don't give them just what we like. We give them 3 choices in terms of, say, gene selected, the top ranked, the middle rank, and randomly chosen. And we ask them to choose. We don't give them just one, just because they're not always unbiased. But there's always eventually some human bias left, but we try to be in the interaction with domain experts. So far, my domain experts collaborators haven't failed the test, but they do have confirmation bias like we do.
Great, thank you so much for the wonderful talks. Both are wonderful. So we are reaching the end of the hour. So thank you so much again for this wonderful event. And I think most of people will know your contact. They may contact you offline. Thank you again. Okay, bye.
Thank you for having me.